What we're going to be looking at now is this idea of a matrix, or the plural would be matrices. So a question that we need to ask ourselves is, well, what is a matrix? Well, it's just an easier way to organize numbers. Kinda, if you think about it, like a fancy table. And there's multiple meanings of the information that is held within a matrix. So arbitrarily, these are just random numbers that are organized through this matrix. Each column has a role and each row has a role. So generally, we label matrices, we label matrices with capitalized bold letters. And in this case, we used A. However, matrices are also classified by their size. So what makes them up? How big are they? I know that I have 6 elements inside that matrix, and they're organized into rows and columns. So how do I determine its size? Well, I actually use the dimensions of the rows and the columns to classify its size. So because we use rows and columns, we use always the rows first, going down. So I can see that there are 2 rows, so I put a 2 in there. And I can also see that there are 3 columns, so I put a 3 where the C is. So our matrix A is a 2 by 3 matrix, which, when you actually multiply them, has 6 elements inside the matrix. We can identify elements, particularly if we were curious to see the information that was being held within the matrix. So, for instance, of matrix A, element 1, 2. So that 1, 2, the same way that we use to classify the size of matrix A, we actually use that both rows and columns to find the certain elements. So row 1, column 2. I go to row 1, column 2, and my element is 0. Let's try another one. 2, 3. So I need to find row 2, column 3, and my answer will be 5. Matrices behave and have tendencies like any other number. It's a way to organize numbers, so they have operations that can be formed on them as well. You can add and multiply matrices the way you add and multiply numbers, except it gets a little bit tricky because there's some rules that you have to follow. Let's first take a look at the addition of matrices. So if I start with matrix A, and it's going to be a 2 by 2 matrix, and then a matrix B, which is going to be another 2 by 2 matrix, I can fill in the elements, and you can see that I have 2 rows, 2 columns in each A and B. If I wanted to take matrix A and add it to matrix B, well, I can, because they're both 2 by 2 matrices. The first element of our answer matrix is going to be a combination of the first elements of each of our adding matrices. So I take row 1 element column 1, and I take row 1 column 1 of both matrix A, matrix B. So you can see that my element 2 in red is being added to my element 2 in blue from matrix A and then from matrix B respectively. So the next element that I'm going to be looking for is row 1, column 2. So I take that corresponding element from both matrix A and matrix B in order to find my solution matrix. I continue with my bottom row. Element 2, 1 is from row 2, column 1 of A and row 2, column 1 of B. So it becomes 1 plus 3. And then finally, element 2, 2 comes from the second row, second column of each matrix. I can take each of my elements and simplify them now. No longer do I need to have this expression for each input or for each number. I have 2 plus 2 is 4. Then I look over to 1, 2. 4 plus a negative 1 is going to be 3. 1 plus 3 more positives is a 4. And then finally, 7 added to a negative 1 is going to leave me with 6. But does it work if we go in reverse? What if I take my B matrix and put it in front of my A matrix? Will the rules of addition apply, and will it be commutative? Well, the answer to that is absolutely. It is commutative because of the fact that we are adding the elements and bringing them together. It is commutative. Just to reiterate that addition of matrices can only happen when the matrices are of the same dimensions. I can't take a matrix that is 5 by 1, which means 5 rows and 1 column, and add it to a 2 by 2 matrix, 2 rows, 2 columns, because that long column and that square matrix, they don't have corresponding elements, so they can't be added together. Since we can add matrices together, we can actually have an additive inverse of a matrix as well. So I wonder if the rules apply and those questions still apply that we use with addition, if it would apply to matrices as well. So the question we would ask ourselves is, how do we make 0 pairs from these numbers? Well, a matrix is just a way to organize numbers. So however many elements are in your matrix, we make that many 0 pairs. But we're not making 0 pairs, we're actually trying to make 0 elements. So if I take my matrix A and add it to the inverse matrix, I should be able to get the identity. And the identity of addition is still going to be 0. I need to make my 0 elements. So I'm going to copy down my matrix, and I'm going to keep my identity. But how do I go from my original matrix to zeros? Well, I apply the inverse of the numbers in the matrix. 2 plus a negative 2 would give me a 0. 4 increased by a negative 4 would give me another 0. 1 plus a negative 1, a third 0. And 7 plus, oops, that should be a negative 7. Let's fix that real quick. Would be another 0. So when I have my negative matrix, that is the additive inverse. It's the same size dimensions, it's a 2 by 2, and when I take that inverse matrix and I add it to the original matrix, it will give me the identity matrix, which is full of zeros.